Hello everyone, once again. We will continue with chapter 4, section 2, that is the conservation of mass, or as I call this as the mass balance. Since we are studying the control volume, we have the entrance or living mass, okay, to the system through system boundary. So the conservation of mass or the mass balance is important in that sense. And let me start with the fundamentals of the mass balance. For control volume, let me put a schematic over here. Consider a system, whatever the system is, with the system boundary as such. Okay. And it has the incoming mass, m dot in. I put the subscript in here, but some textbooks just put I, that stands for inlet as well, and m dot out over here. And again, some textbooks put subscript E, stands for exit. So m dot out or m dot E, maybe I should write it here. So this can be written as m dot I, this can be written as m dot E. They mean the same thing, okay? So we have the incoming mass or out. And what we are interested in is what happens to the change of mass of the system. So it means within the system boundary with time. Okay, so we are interested in that one. Therefore, the amount of mass of the system, the change of that with respect to time is nothing but equal to m dot in, how much mass that enters, minus how much mass that leaves the system. Okay? Therefore, this right-hand side is the mass flow rate crossing the system boundary. Okay, so basically m dot in is the mass that enters the system through system boundary. M dot out is the mass flow that leaves the system through system boundary again. So if there is any mass flow within the system, okay, so say this particle over here gets into here, it's also a mass flow, but we are not considering that one because it doesn't cross the system boundary. Okay, so we don't consider that as the mass flow. We just consider the ones that cross the system boundary. That's why the definition or how you draw the system boundary matters. It is important. Okay? And then the left hand side is the time rate of change inside the system boundary. Okay? So this is the one, but if I were to generalize this one, okay, this is just if you have a single inlet and single exit as we call. So it means you have the mass flow that enters the system at a single point, at a single location, and the mass flow at a single mass leaves the system at a single location as well. You might have multiple inlets as well. And you might also have multiple exits. Okay? So if that's the case, there's nothing too complicated. Okay? You sum them up. You sum the inlets and you sum the exits. That's it. If you have multiple of them, you sum them. Okay, so this is the more generalized form of the previous one. Okay. So the simplification is if your system is operating at steady state. Okay, so at steady state, dm by dt is equal to, let me put the general form, the summation of the inlets, the summation of the exits. If you have multiple inlets, multiple exits. At steady state, this part is basically zero because by the definition of steady state, no mass accumulating or depleting within the system. Okay? So there is no mass changes. Therefore, it means, as you can see from here, from this equation, the m dot ins are equal to m dot outs. So the same, if we add some energy to the, so not energy, if we add some mass to the system, the same amount of mass leaves the system. Okay, so there is nothing, no mass changes of the system. So this is steady state. If you have a transient system, sometimes this is referred to as unsteady, so opposite of steady. Okay, that is unsteady, but typically I use the term transient over here. So let me write down the one in general, the conservation of mass in general. Okay, so what you do is you would like to know how much mass basically accumulates or depletes over time. Since this is transient, the mass of the system might change over time. So the left-hand side can be or may be non-zero. So what you do is, first of all, you multiply both sides with dt. Okay, and then you integrate all these terms, and the left-hand side becomes delta m, which is m2 minus m1, which is, so this is from m1 to m2. Okay, so this is from time 0 to a time, or maybe I should say from time 1 to time 2, if you wish. So this left-hand side becomes nothing but delta m. And once you integrate this, the first term on the right-hand side, it's going to be the total m dot in. And this becomes the total m dot out between times t1 and t2. Okay, so this is basically, for instance, the total mass enters the system through system boundary between T1 and T2. Basically, what I'm saying is, for a process occurs between time 1 and time 2. And consider that for, if your delta t, T2 minus T1 is 10 seconds, okay, if I add you 1 kilogram for each and every second, so m dot in is like, m dot in is 1 kilogram per second. For over 10 seconds, I added how many kilograms? 1 kilogram per second times 10 seconds. So that's basically 10 kilograms. So m in is 10 kilograms for that one. Okay. So similarly, m out is the total mass that leaves the system through system boundary between time 1 and time 2. So delta m is the difference between those two. So this is very similar to what we covered for the control mass systems, or before that one. Okay, so for the control mass, the left hand side was 0, the right hand side was also 0. The left hand side was 0 because m dot in is, or m in is 0, m out is 0 for control mass, therefore m2 was equal to m1. Okay, but with control volume systems, you might have m in, m out, therefore the left hand side may be non-zero. So please keep this in mind. And section B is the mass flow rate. So sometimes, especially for liquids, the mass flow rate is not measured. What is measured is typically like the volumetric flow rate, okay? Or sometimes it is speed. So consider a section of a pipe as such, the center line. Okay. So consider this as a pipe. It has the cross-sectional area, okay, that's like A, let me put X to denote that that's cross-sectional area. So area that has to be perpendicular to the flow. Okay? Therefore, you have the flow that enters the pipe. Okay, say it has the speed of V. Okay, and I have the cross-section area, I have the speed, and I'm interested in what is the flow rate. Okay? So the definition or the equation to calculate the mass flow rate, if you are given these, is you have the speed. Okay, so this is the V for the velocity, it's the vectorial, right? So you multiply this with the cross-section area, AX, so there's multiplication over here, and you divide this with the specific volume. All right, so this V is the specific volume. Volume of the fluid that passes through the pipe. Okay? So if you check the units, you will get meters per second over there for the speed. This is going to be meters square as the area, and the specific volume is what? Meter cube per kilogram, right? So as you can see, meter cube will cancel out this meter cube, and you get the unit of kilogram per second, which is the unit for the flow rate, mass flow rate. Okay? Is m dot. But as I mentioned you, most of the case, the mass flow rate is not measured. If the speed is given to you, this is the equation that you can calculate the mass flow rate. You need to know the cross-sectional area, which is the perpendicular to the flow. Okay? And you need to know the specific volume or density of the fluid in general. Okay? Remember that specific volume is not about 1 over density. That is the reciprocal of density is specific volume. So sometimes you know density, sometimes you know specific volume. In our thermodynamic tables, which is the appendix of your textbook, the specific volumes are tabulated. But especially for liquids, instead of measuring the speed, they measure the volumetric flow rate. Okay, so sometimes you might hear that like it consumes like 10 liters per hour. So liters per hour, meter cube per second, these are the units for volumetric flow rate. So they are typically measured with the flow meters, and the units are nothing but like meter cube per second, liters per hour, liters per minute, so on and so forth. Okay? The symbol that we use for the volumetric flow rate is nothing but V dot. Okay? V is for the volume. When we put a dot on top of that one, it's going to be the volumetric flow rate. Okay? So the definition is as such. Consider the same pipe flow as before. So V dot is going to be speed. Use a thinner pen. Okay, V dot is equal to the speed of the flow times the cross-sectional area. Okay, so when you check the units, it's going to meter per second times meter square. So it's going to be meter cube per second as the unit of the volumetric flow rate. And you can convert meter cube to liters. It can be liters per second. You can convert second to minutes or hours. So it can be like meter cube per minute, meter cube per hour, or liters per minute, liters per hour. All these are the units for volumetric flow rate. So As you can see, when you compare these two equations, okay, you can convert volumetric flow rate into mass flow rate. So, for instance, the mass flow rate is volumetric flow rate divided by specific volume. Okay? So, you can convert mass flow rate to, volumetric flow rate to mass flow rate as such, or typically, because if volumetric flow rate is given, you need the mass flow rate, so you can do this. Or you can say the volumetric flow rate is nothing but the mass flow rate times the specific volume. If you know the mass flow rate, but you need the volumetric flow rate, this is the conversion as well. So that's pretty much it about the mass balance and the mass flow rate as well as volumetric flow rate. Okay. So I will stop the video here. In the next video, in section 3 of chapter 4, we will go into the energy balance, or the first law of thermodynamics for control volume specifically. Okay. As usual, let me know if you have any questions. For now, that's all from me. Take care. Bye bye.